So. Gut. Okay, I think the microphone is again a little bit, needs a little bit of boosting. So if it's like last week, this should be good. Yeah? I need some visual feedback. Is this the right audio level? Should be louder. Is good? Oh, whoa. Bitte warten, Beamer wird heruntergefahren. That's exactly what I wanted, right? That's, this wasn't me. This wasn't me. But, oh, man. Okay. Well, yeah, then I was completely set up. I mean, that's it, for the third rehash of the hybrid setup that we were seeing here now in 3 weeks. Audio works, the video works now. So on Zoom, people can see me if everything is correct. We're live on YouTube. Everything is perfect, except that we don't have a Beamer currently. Projektor ein. Beamer wird gestartet. Ja. Good. Let's see. What can we do in the meantime? It should be warm, right? And that's, so it should start to project really quickly. Because I can start to give like a rehash of what we did last week's, but come on, we didn't do that much yet. So if you really have completely forgotten, then it's almost too bad. But as much experience as I do have in lecturing, both managing devices that I don't use on a daily basis and do it. Come on. Yes. Yes. Okay, good. So now we can get properly started. Okay, welcome to November 4th, 2011. 2021, not 2011, but I'm sorry. I mean, it's 16 hours late for this welcome, but then again, right? I mean, do enjoy this day to the fullest. Third lecture of EML, and we're going to continuing on the spectacular topic of linear regression that we embarked upon last week. And what did we learn last week? As a very quick recap, we essentially learned that if I throw some data at you, right? I mean, that's some data over some variable x that we've measured, and we're particularly interested in finding a linear function that predicts some output variable y, how to find, well, the best linear function, how to find the two parameters, the two coefficients, beta naught, beta 1, the intercept and the slope, such that we can optimally predict what y is going to be given some input on x, right? Combining that with what we learned the week before, we know that, well, if we're dealt a good hand of cards, meaning we're given data where actually the true underlying function is indeed linear, and we're given, well, enough data points, not just 2, then actually we have a very good chance at finding the true function. And the more data we have, the better it gets, right? We know there is this concept of reducible error. That is essentially the error that, given more data, we can actually get closer to the true function. And there's the notion of irreducible error. Noise intrinsic to the system, and we can't hope to beat that, right? We also had the notion of bias and variance, and hopefully you remember those two go hand in hand with what I just said. If the data was not generated by a linear function, and you're now going to fit a linear function on top of it, well, no matter how much data I give you, you will never be able to find the true function, right? You're biased against it. There's a very huge bias. The error that you make well, there's basically a threshold you never can really go beyond, right? That, regardless of what the irreducible error is, right? The noise in the process. Okay, so this is essentially a mismatch. Okay, so that's actually, so somebody from the back in the hall been asked if the volume can go up. Is this a question that is still, so if you're asking that over Zoom, this is amazing. I mean, that's really modern times. Should the volume go up further? Or are we now good? Up? No. Okay, yep. I'm not responsible for any hearing loss, right? I mean, that's, okay, this, I can't push it up higher, so I hope this suffices. I'm not gonna shout, because then my voice just deteriorates very quickly. Okay, anyway, but getting now feedback over Zoom, I mean, amazing. You could have shouted, right? I mean, that's, or raised your hand. I mean, that's, I know it's very 2011, but still. Good. Okay, so that was linear regression in a nutshell, up to n, and that was roughly halfway last week, right? What I now just recapped in a few sentences. Then afterwards, we said, okay, you know what? One variable x, right? I mean, I have more data, right? I can measure more things. There's more genes to measure, or I mean, I can take into account the weather from yesterday, or from the day before, and the temperature, and the air pressure, and whatnot you might want to use to predict the stock market of next week, right? So can we do linear regression with multiple input features? And yes, we can, right? It was relatively straightforward. What we saw previously, just with some linear algebra, some flopping around, we can actually get the optimal coefficients pretty much directly from data, and after some linear algebra kung fu. And that's where I left you, pretty much, right? And that's where we left each other, you could say, last week. So let's pick it up right there, because I already hinted at that we're gonna discuss 4 important questions regarding linear regression, and particularly multiple linear regression. So we have some data, and one of the questions we could ask is, at least one of the predictors we have, is it useful? Right? I mean, if you only test everything one by one, then you know how to do it. We did some significance testing. But, well, if we just give a whole ocean of variables, what can we do? If there is at least one that is significant, which ones, if perhaps there are more, which ones are the ones that are significant? How can we find those? Well, painfully, I can already predict that. If we now fitted a model, and we see that it predicts something beyond just complete random guessing, I mean, well, how good is the model actually? Can we give a quality measure? I mean, how well does the model fit the data? And last, but definitely not least, now that we have a model and it seems to fit the data very well, how accurate is it actually in predicting individual cases? That might seem a bit like, yeah, but hey, wait a second, we're trying to maximize model fit, minimize error, right? I mean, the best we can. Yeah, but okay, how good is this? We have discussed confidence intervals over the parameters. So we know, right, in 95, under certain assumptions, in 95% of the cases that we can think of, the parameter we found falls within a certain interval. That is amazing, of course. That says something about how stable your learning procedure was. But it doesn't say anything about if you make an individual prediction, like what's the stock market going to be tomorrow, right? Or does this particular patient, I mean, do they have a chance of getting the bad disease or not, right? How big is this chance? That's what we actually would like to know in practice, right? Not just some average. I mean, in the end, everybody's going to die, but you kind of want to know, right, if you're in the hospital with a bad disease, so in case it's going to be tomorrow, next week, or when I'm old and gray or hairless. Good. Let's go from the top. Is at least one predictor useful? It comes down to significance testing. So we're just going to reuse a large part of the machinery we saw last week. Namely, we have the hypothesis test that the null hypothesis says none of the predictors, none of the x's are any useful. So that means that if they're not useful at all, the coefficients for these predictors should all go to 0, right? Because only if they're useful we want actually some signal from. And the alternative hypothesis, H alpha, is hence, well, at least one of these betas is non-zero. We could, in theory, do this all one by one by one by one by one, and you would not have a good time. Not just because it's a lot of work, but you fall into the trap of multiple hypothesis testing, and that is something that we'll discuss in a few slides. So what we rather do, let's just do multiple regression. Let's throw all these predictors in. Let's find the best model. And then we can look at the F statistic. The F statistic is simply the total sum of squares minus the residual sum of squares. And we divide this by p. That's in order for now. what does this say? Well, if we somehow magically have the correct model, then the total sum of squares and the residual sum of squares divided by p because we have p predictors will actually tend to the variance of the data, variance squared. Right? So the expectation, still need to get used to that. That can't just point at the screen here. So look, this term, oh wait, no, oops, this term here will tend to sigma squared. Okay, that's amazing. The numerator denominator, that's the residual sum of squares divided by some magic number, and that one tends also to exactly variance squared. Okay, so that means that, hey, if we somehow magically have the right function, 1, right? 1 is the magic number. If we get an F statistic of 1, okay, it's perfect, right? I mean, that's we actually we are spot on the assumptions. So then H0 is true, right? I mean, there is no beta that we can get anything out. Okay. What is this P, and particularly what is this magic number n minus P minus 1? This is a question that already last week somebody asked in the RSS in order to get to the variance, and just using the standard error and such. There was this, well, n minus 2. Where does the 2 come from, right? And then I cheated a little bit. The student already gave the answer. I'm not sure if I see that student. Maybe he was so disappointed in my answer that, well, actually, the answer was good. The answer was good. So if you're disappointed, it's on you, not on me. You could think of it that the minus 2 was that, well, we're trying to fit a linear model. So we need at least 2 points. If you have fewer than 2 points, I mean, there's no way you can come up with any reasonable line, right? And that was the answer. Okay, yes, that's a good answer. Actually, what it comes about is how many parameters do we have to estimate? And not so much the line, right? But how many degrees of freedom do we have in the model at all? And for each, I will need at least 1 data point. Otherwise, yeah, it can't fit any model, right? But that is exactly what we do here. We have n minus p, right? I mean, we have p parameters, and we always have the intercept, beta naught, right? Beta naught is, we get it for free, even if we have no predictors. So that's the minus 1. So in the bivariate case, where we have just x and regressing towards y, then, well, we have 1 parameter, and beta 1 for x, and we have the interceptor that is 2. Right? You can think of this as a line, but you can also think of it just in this n minus p minus 1. Good. Okay, so we can compute this F statistic, some magic number, and we know that if it's 1, then our null hypothesis holds. And because, as we see at the bottom, if actually the expected value, oh, oops. Keyboard is sticky. Literally not like sticky, but sticky, sticky. Not that disgusting. That's it. Don't get this crown of your face. Good. If the total sum of squares is larger than the residual sum of squares, well, that means that there actually is more structure that we can tease out than we should be able to if all the parameters are 0, right? It's not just the noise in the data. Then the expectation will be higher than the variance. Right? Okay, so that means that if we get an F statistic that is higher than 1, that gives evidence, that shows evidence that, well, our null hypothesis might not hold. Now, for the advertising data, if we just run it with, what is it, news, TV, radio, right, in one go over all 3, we get an F statistic of 570, and 570 is larger than 1, so you should, hey, we have some evidence. But hey, we want to do significance testing. I mean, is 570 large enough? By gut feeling, you can say yes, but okay, let's make this a little bit more precise. Here we have the probability density of the F statistic, of the F distribution, to be precise, for a number of different data sizes from 1, 5, 2, 5, 10, and 100, and for a different range of predictors, 2 up till 100. And as you see, I mean, you get sort of like a Gaussian shape. I mean, it tends to go towards the origin, and that looks a bit more exponential-ish. You just simply fill in the F distribution how many data points you have, how many predictors you have. You get a curve like this, and that now allows you to calculate what is the probability of getting, in our particular case, 570. Well, as you can see, that the gray one, I mean, that tends to 1, that is quite standard, starts to become more and more narrow. It's also what you're going to get. And hence 570, the probability of drawing 570 from this gray line, and this is almost 0, right? Let's call it epsilon, right, just to make the mathematicians happy, but Is this significant? Yes, right? There is really something in this data. Good. So at least one of the predictors is useful. Brings us to the next question. Which one or which ones is it? And how can we get something well, out of this data in that sense? And I know that you know, because we did this last week, TV and radio, yes, and newspaper, no, right? But now we're just taking a slightly different approach to figuring this out, which also works if we have many more predictors. So we have a slightly different hypothesis than we had previously. Right now, we don't have the null hypothesis that all of the betas are essentially worthless, right? We assume that all should be 0. What we actually now assume is that for the first so and so many predictors, they should not be 0. Those are useful. But then for the ones that follow, those are useless, right? And the number that follow, well, this number we're going to call Q, right? So the last Q predictors are useless. That is essentially our hypothesis, which requires us beforehand to specify what is the value of Q. How many do we think are useless? Well, we could start with 1, and then with 2, and with 3, and so on and so forth. There's one tiny little detail that we should not forget. We're now thinking about a sequence, right? We have an ordered set of predictors, because otherwise we can't take the last Q, right? So somehow we need to magically have an order where we have the ones that we think are the most useful up front and the least useful at the back, right? Or magically find the order that through some algorithm. We don't have this. We just assume there is an order, right? The experts know what the order is. By the way, just a small aside, I know I should not do this in the interest of time, but so my research focus is on exploratory methods, right? I mean, not specifically on this. And in exploratory methods, we want to learn something about the data, right? We really want to do inference. And because of that, I am particularly allergic to parameters. Any algorithm where I need to set a parameter, I mean, I hate it because I have no clue, right? And neither do you, maybe because you don't know the algorithm even that I have in my mind right now, but even if you would, you still don't know because yeah, this differs from data to data. Parameters are an easy way out. I mean, they're a necessary evil because we who design algorithms can't solve all problems in general. But the moment that there is a parameter, it's a bit like what Elon Musk says about user interfaces. One button means a failure of user interface design, right? I mean, everything should be completely natural and embedded. Same thing with parameters. Whenever in a research paper a new method is proposed, right, be it statistical, be it algorithmic, and there's a parameter, it's often either explicitly written or left implicit that, well, the domain expert will know how to set this parameter. I've worked a lot with domain experts, and I'm yet to meet the first domain expert who is able to set any parameter. Because when I then come to them, okay, I want to find clusters. How many clusters do you want to find? Like, I don't know. That's why I ask you, right? If I would have known that, then I would have done it myself. Like, yeah, number of clusters is like one of the most basic parameters, right? Similarly, well, what should be Q, and what should be the order of my predictors? If they already know that these are the most important, these are the least important, they can probably do it themselves, right? So already requiring an ordering of your predictors is presumptuous, it's ridiculous, right? Then again, we have to do something, we have to start somewhere. This is where we currently are. End of the aside. Okay, so we have our magic order. And now the null hypothesis is that the last Q are useless. So what we're now going to do, what we now can do, is adapt the F statistic, where we now look not at the total sum of squares, but the residual sum of squares minus at 0. And 0 is the one that incorporates all. I can point like this. Just the people on Zoom don't know what I'm pointing at. But I mean, if I'm talking about the RSS 0, so then they can infer it themselves, I hope. Where we just exclude the last Q variables. Now, we have the same idea as previously with the TSS minus the RSS, namely if the last Q are indeed useless, well, they won't contribute anything, right? And the RSS and the RSS 0 will be the same, so this thing will again tend to sigma squared. Okay, very good. The bottom part doesn't change, right? So it's just a slight adaptation of the F statistic. We already know how to look it up, the F statistic, but we're now going to do it slightly differently because the F statistic and the F distribution are tightly linked to the T distribution and the T statistic. And the T statistic you already knew, right? We had in the table last week, where, well, higher numbers meant significant, right? I mean, that's low numbers bad, high numbers good. So intercept in this particular case was good. TV and radio very significant. If we added newspaper in addition, not so good. What is now the relationship? Well, the t-statistic is essentially a trick on what we have here on the slide, where we one by one take out one of the predictors. So you could say that we consider, in this particular case, 3 different orders. One where we have TV, radio, and newspaper last, and that is Q is 1, right? So that's the last one that we take out. We have, alternatively, TV, newspaper, and radio is last. And last but not least, we have the one where TV is then last, right? So what is the added benefit? So it's 2 strategies that kind of do the same thing, except that what we have here on the slide really looks at a chunk, a group of number of predictors, and previously we were just looking at things one by one by one. Okay, and then the square root of the statistic, I mean, that essentially comes down to the t-statistic. I mean, that statistics is all the same in the end, right? And that's just large numbers. Okay. This is one way how to do this. Is this particularly satisfying? No, I don't think so. I mean, I like algorithms. So, well, that's where we go in the end. But there's one other problem. From statistics, whether you take StatLab, or you took MFI3, or any other statistics course, you hopefully have come across to the multiple hypothesis testing problem, right? So for those of you like, okay, yeah, what was it again? Let me try to rehash a little bit. What does a p-value say? The p-value is the probability that an observed effect, right? Like, oh my God, I mean, my parameters, right, they look so good and my prediction is so amazing, right? I mean, and I get a p-value of 0.5. What does this mean, right? I mean, should I be happy or not? Obviously no, right? I mean, otherwise I would have chosen a different value. But 0.5 means that there is a 50% chance that the effect that you've observed has been generated by the null hypothesis, right? So basically in 1 out of 2 cases that you draw the same amount of data, you will find the result highly similar to yours. If you have a p-value of 0.05, okay, well then only 1 in 20 data sets generated by the null hypothesis would actually lead you astray. If you have a p-value of 0.001, right, 1,000, only 1 every 1,000 data sets, the null hypothesis would generate blah, 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 and so on and so forth, right? So lower p-values are good. That is a test for one hypothesis. And it's really just a chance that you draw the wrong conclusion. Now, if on the same data, we do not test one hypothesis, but we test many, let's say 100, 1,000, 1,000,000, and for each and every single one of those, we again have this risk of the alpha threshold, right? The acceptance threshold. Let's say we set alpha at half. Or let's actually stick with 0.05. That's so 1 in 20. So for the first hypothesis we test, we have 1 in 20 we accept it wrongly, right? For the second one, same thing. For the third one, same thing. So what is now the chance, if we keep on doing this for more and more hypotheses, that we accept at least one wrong hypothesis, I mean, a spurious result, that, oh my God, it looks amazing, but actually it was just completely random, that goes very quickly, that probability goes to 1. So that means that if you're not careful, you're going to run to your expert like, oh my God, I found something, and yeah, okay, they're not going to be happy, right? But, so of course you could say, let's now just adjust alpha down a little bit, which is a very crude way to do multiple hypothesis correction. Ponferroni correction is essentially the idea. The problem is now that if you have relatively little data, it is of course highly unlikely you can get a very low p-value, right? There's just nothing that can give that, right? So that means that if you're going to be testing many hypotheses on small data, you can just as well just stop before you start it, because nothing can be found, right? Unless you apply really smart techniques. That, in a nutshell, is the problem of multiple hypothesis testing, and is still one of the key research foci within statistics. Not necessarily mine, but plenty of people have a pretty good paying day job to fix this. So let me just now go over the slide and just essentially repeat with the slides what I just said. But first I'm going to take a sip. So suppose now that we have 100 predictors, and we generate, and the null hypothesis is true, right? I mean, we have 100 predictors, and they are all, so there's no relationship from each predictor to the actual output, right? We generate some random data. Now, if I do this often enough, if I generate not one data set, but many, on one or many of those data sets, I will find at least one coefficient that is significant, right? I will draw the wrong conclusion, even if the true model is complete bogus, it's complete noise, right? Now, the t-statistic that we've seen does not take into account the number of predictions. So this is why it's a little bit icky to apply directly. The f-statistic does. Is it now the best way to adjust? Not necessarily, but let's ignore this for now, right? Right now, we're happy. One of the problems becomes, in our particular case, if we now have more predictors than we have data points. This is a problem I've been ignoring for now. Perhaps some of you already thought of it. We're all of a sudden really up excrement creek without the proverbial paddle, right? I mean, not. One, the matrix that we want to invert to get our estimates of the betas doesn't work anymore, right? So that is one problem. Well, let's assume that we can fix this. We have another problem that there's not just one single solution, there's many solutions, so we don't know really which one to choose. And yeah, then the f-statistic also can't pick up which one is now most significant. It will just say, okay, we have a number which are a number of possible results which are good, and significance is not going to help us anymore, right? So p larger than n is very scary in many cases. However, you very often encounter this in real life. You very often have just simply more things that you can measure. You have, for example, look at images. You have a ridiculous amount of pixels, right? If you look at a high resolution image, then you would need an exponential number of images of that resolution in order to compensate for this. This is reality, p larger than n. We're now going to ignore this until chapter 6. How can we now select important variables, happily ignoring the previous case? Well, very often we find that although we have many predictors that could possibly steer the outcome, in practice there's only very few that are really important, or very few that are important at all, right? So most can actually be ignored. So that then gives rise to what we call feature selection or variable selection. There's many different flavors of it. We're again going to discuss this when we go into high dimensional data. But let me just give you a very quick primer, right? Just to whet your appetite as well as to quench your thirst for, okay, well, why wouldn't we just do this or this or this? First thing that we could do is simply enumerate every possible subset of predictors, right? So we tested without any predictor, we tested with just TV, just radio, just newspaper, every pair of predictors, and so on and so forth. Well, how many are there? Well, it's just exponentially many, right? I mean, that's not so bad, just 2 to the power p. So if we have 30 predictors, then we have, well, more than 1 billion different models, right? I mean, you can kind of see that this multiple hypothesis testing problem bites us in the back really quickly already, because 30 predictors is not that many. Right? But I mean, remember the story I told about the cancer case, right? Or the cancer, where we wanted to find with the treatment that is really good for a certain type of patients, but really bad for all others, right? And then we had 40 or 42 predictors, something like this. Yeah, well, it's already many. But, and we only had, was it somewhere between 150 and 300 patients, like rows in the data. So there's no chance that we will get a p-value of 0.0000001, right? It's just impossible. And yet we want to get something out of the data. So one of the problems that we now face is suppose that we actually just simply fit each of these models. And now we want to find, well, what is then the best one, right? And can we identify this somehow? Well, we cannot use the training error. And that is currently the only tool that we have. We just have some training data. We fit some parameters, and we know these parameters are the best fit for the training data, and we can see how much error we make on the training data, but that is essentially the only tool we currently have. I'm pretty sure that all of you can already think of ways on how we can circumvent this, but right now we're just going to play dumb, right? We don't know how to access the red line over here, the test error. We're going to discuss this later. So, but regardless, because of this combinatorial explosion, this 2 to the power p, it is almost impossible to do subset selection, A, computationally. There's just way too many models to evaluate, and B, then to determine which one is truly best. we need a different paddle or a different floating device. Probably if I would have given this as an assignment, here is a number of predictors, find me the best set of predictors, right? I mean, that without necessarily any guarantees, you probably would have come up with this algorithm. Let's start with the empty feature set. With the empty feature set, you only have one coefficient, beta naught, the intercept, right? The average value. So you can already do some prediction. It will suck, right? But okay, you can already do some prediction. And then what you can do, you can iteratively add that predictor that improves whatever you're trying to optimize most, right? If you're trying to reduce the residual sum of squares, well, okay, then just with the empty model, add x1, see what it does, add x2 instead of x1, see what it does, and so on and so forth, right? Take the best one, rinse and repeat. Okay, that's forward selection. That works. It's one of the staple, one of the standard methods in feature selection. It has some very obvious drawbacks, but I'm not going to go into the detail right now. If we can do forward selection, then we can also do backward selection. And probably the other half that just said, okay, no, I would never have done forward selection, that is stupid, would have probably done backward selection. Namely, let's start with everything and then just throw out those predictors that are insignificant, by which you mean for which the coefficients are insignificant, right? They do not add sufficient information. For example, F statistic, D statistic, whatever you like, right? Okay, and then you stop when some criterion is fulfilled. Again, a bit of black magic. We'll solve this in a later chapter. For example, you say, okay, I want to have that the variance, the unexplained noise in the data is not above this, or I want to have at most so and so many features, whatever, right? We'll just ask the expert. They will know what they want. If we have those two, then perhaps there were a few of you say, okay, but why don't we just do both, right? Why don't we first grow? And while we grow, it might be that we now pick up a few predictors that are dependent on one another. They're correlated. So yeah, they do add a little bit, but one of them can actually later go, right? But, well, that is mixed selection. We first grow, then we shrink again, then we grow and we shrink until convergence. Easy peasy, right? But computer science and data analysis, it's almost trivial at times. Good. Next question. How well does the model fit the data? For each of the cases that we just discussed, well, we have a different model and we want to see, okay, how good is it now actually? Like I said, I'm not going to give you the secret for how to assess test error properly, but I can give you this. The most common, I mean, so this is straight from the book, is the residual standard error and the residual in, well, the R squared. I have to admit that I had to look up what the RSE was again, because it's so commonly used that, well, I forgot. Anyway, the RSE we have already seen is essentially just the squared of the standard error. And that is and with a few mathematical fluffs, but that is essentially what you do. We're going to ignore it for now. We're just going to look at the R squared, which is the fit that you get, is the value that you get when you do Pearson correlation. Right? Pearson correlation we already encountered in the first lecture, right? We have two variables. Essentially, it's how well does a straight line fit the data that we have. Now, for univariate regression, this is very useful because, well, we just have x, we have a predicted y, and then, well, the correlation between them squared, that is the R squared. Yeah, that is how well does it fit it. Right? You can also even do it without that, but then it becomes a little bit more important. For multivariate regression, we don't have the luxury of being able to compute in one go the correlation between, well, the x, because there's many of them, and Pearson correlation only allows for two variables, so one x and y. So what we can instead do, we can look, okay, what is now the correlation between the true values of y that we should have predicted and the ones that we predicted. And obviously, the closer those get, then we have a straight line, then Pearson is going to be super happy, and we have an R value that is very low. Okay, now, I coupled together the values that they give in the books, and for some reason, they do not give me the F statistic value for TV and radio, and I was too lazy to compute it myself. I admit that immediately. I'm busy with research, right, with science, and that's an F statistic for TV and radio, I mean, screw it. Okay, so I should not have said this, right? This is going to come back in the evaluation. I mean, damn it. What are we now going to get? Oh, I have a question here. I mean, that's what is R squared exactly 1? What if this R squared is exactly 1? well, then we're super happy. We're super happy if r squared is 1, because if it's 1, that means that there's a perfect linear relationship. If it's -1, it's also a perfect linear relationship, but, well, it has a negative slope, right? If it's at 0, it means, what is this? I don't know even, right? That is essentially what Pearson then says. Pearson will say, what is this? I don't even, for example, when your data is nicely clustered into 2 blobs or 3 blobs. Basically, a straight line is not going to explain it at all, right? And it will give you a 0. It's basically explaining or telling you, like, there's nothing to see in this data, which is complete bollocks, right? So don't trust Pearson correlation, right? The man himself is dead, so it's whether even Ouija board or whatever you mean, that's I would still then also not trust the answer. Okay, good. So, but that hopefully explains what is r squared to zoom. What we now have here, for different models, we have then the RSE, the r squared, and the f statistic. And what you now see is something that hopefully does not make you happy. Namely, that for RSE, what is the best value at the full model? For TV and radio, well, it's only a little bit higher, right? But still, if we are going to afford the lowest, we go for the lowest, right? And there's no choosing for TV and radio. So we can see that, well, there is some information, and this is a pretty good model. But for r squared, hey, look, we have for TV and radio a minusculely better model, coincidentally in this particular case. I mean, in general, I mean, forget about it, right? I mean, it's not that all of us an r square you can trust, but what you do see is that the difference from full model and TV and radio is very, very small, much smaller than from TV to TV radio, right? That is a much larger jump. So that shows you that, hey, adding radio really gives some information, and adding more, yeah, barely anything, right? And that's, so be careful. With r squared, it always increases. Same thing with RSE, or RSE, no. But, actually, yes. Lower is better, higher is better. But thinking on your feet is difficult. So if we add more, in general, it just goes up, up, up. Because you can always squeeze out a little bit more information. You can overfit more and more and more, right? Because we're looking at the training error, not at the test error, not at the generalization error, right? And r squared doesn't know anything about test or holdout data or anything of that, so yeah, too bad. Chapter 5, then we're going to discuss test error. And I hope that I can now stop teasing you about the test error. What I can offer you in the meantime is to, well, just plot the data. Look at the data. This is one of the best advices that I can give you when you're dealing with statistical learning and so on and so forth. Inspect the data, plot it, look at it. You will see if something is good or something is wrong, if you're on the right track or not. For example, here, so this is a 3D plot in sales, TV, radio, where I plotted the plane that what we found, right? So the 3 betas that we have. Okay, we have a nice plane, beautiful. Actually, let me just ask the question into the room, or Zoom, whoever is first. Does this data look linear to you? So what I plot is the plane, and, well, the red dots are then the actual data points. And I also draw, like, the black lines, just like in the first lecture, towards the plane. So Lo says, yes, it looks linear. It's a bit difficult to see, perhaps, but I mean, yeah, so I see, yeah, you in the room. Exactly, you can't see the points on the other side, but what you can see a little bit, I mean, it's still a bit tricky. Let me point you. So here, these points, they are, well, basically on the plane, right? All these points here. Whereas here, where are my points on the plane? And here, where are my points on the plane? And here, I have lots of points very far below the plane. Where are my points? Seems to me that the points are not really distributed like a nice, well, flat band or something, right? Something is fishy. Basically, what we're looking at here, I mean, I can't really quickly remove the plane, but we're looking like a banana in space. That's essentially what we're seeing. If you would be able to move this around, you would see that actually they form more like a banana, right? So a linear assumption that we have here is actually a very bad idea. And now that I mentioned it, you can hopefully see it. And whenever you see now a banana in space, you're like, hey, let's not use a linear model. But by inspecting the data, you can already see that a pure linear model is a bad idea. Okay. we will see very soon how we can fix this, right? So there is something going on between TV and radio that hopefully we can tease out a bit more information. Okay, last question out of the 4, and then we're going for a short break. Confidence intervals. Nice tool to tell us how certain are we about our estimate of a parameter, right? Amazing. Except no expert will be interested in it, right? That's just us patting ourselves on the back, like, look how good a job we did. I'll also soon give you an example of that. It's really just patting on the back, if you hold it wrongly. What you're actually interested in is what is now, let's say, the margin of error if you make one specific prediction, right? Yes, sir, you do have cancer. Like, yeah, oops, right, okay, well, if then it turns out that he didn't, okay, well, he's going to be happy, well, except that, well, he sold all his assets and whatnot, right? That's, and then, oh, oops, yeah, you're not going to die, right? Now you're poor. Or the other way around, like, no, you're totally going to live. And then 2 weeks later, yeah, what is the room for error? Well, there we just have a binary case. In regression, of course, it is more about what is going to be the predicted stock value. And if the prediction interval, we'll see soon what this is very wide, basically mean anything can happen, well, perhaps we should not invest. But if we have a method with a relatively small prediction interval, okay, then we can rely on it much more. So how can we tease that out? Well, yeah, so for the coefficient estimates mean that we can, it's basically the reducible error, right? So suppose that we now have some data where there is a true line and there is some noise around it, right? And that, then given enough data, we will be able to find the coefficients. We know that, right? Thank you, Gauss-Markov, right? That's, or both of them. There's still the irreducible error. That is what we want to take into account into the prediction interval. But for the confidence intervals, we're essentially only looking at what is the range in which we think the true parameter would be, right? And if we only would have more and more data, our estimates would be better and better. So that is the first source of error. Let's take a very quick sidestep, quite literally, to reducible error again, right? Bias, variance, and its friends. If the data is not linear and we're fitting a linear model, we have a huge bias, right? There is a large chunk of error that we can never hope to get rid of. That's just too bad, right? So we can even have very small confidence intervals, but it's never gonna be. So, I suppose that we now know somehow magically, God-given, that the data is linear, right? And we have a certain amount of data, so we can compute our confidence intervals. Now we would like to get, okay, what is now the range in which a prediction could actually fall? Prediction interval does essentially take the confidence interval and then adds a little bit space around it. And the space around it is our guess of how large is the irreducible error, right? This is the reducible error, right? So given enough data, we would be able to squish this to 0. And well, the irreducible error, that is sort of a band around it that we can never really fix. So just mathematically, if you just write it down, confidence interval is the average of y plus t statistic. The a is the percentile, so at 0.95. So how to do a confidence interval, so this should come relatively familiar to you. And what we have here is that we just simply add the 1, because the squared or mean squared error, that will go to the irreducible error, and hence we just lift it up a little bit. We widen the interval. And in the limit, this is exactly the confidence interval plus the irreducible error. Beautiful. Now, looking at the particular case of the advertising data here at the bottom right, we have a confidence interval for sales between, what is it, 10,985 up till 11,528, where the actual predicted value, or the predicted, the coefficient value is smack in the middle, right? That have a certain width around it, whereas the 95% prediction interval expands with what we currently think is the reducible error, and then you automatically always have a wider prediction, or a wider interval as the prediction interval. Still at the same mean, right? Because the mean is essentially what we would predict, right? That is what we think it is, but anything can happen. Good. Confidence intervals, prediction intervals, you will find it in the ESL book, green plus, in higher detail than in the ISLR book. There's also a nice reference at the bottom that you can click on the website, well, the slides that are on the website, and that's to brush it up. This is also relatively standard stuff in statistics, so I'm not going to go into further detail. But it is very useful if you ever want to deploy a method in any application domain. Right? Don't just go for model fit. What are the ranges in which a prediction can fall? Right? Basically, you should always ask of a method, can I trust you? And actually, just like a domain expert should always ask you, can I trust you? Can I trust your method, or what your method says? And the honest answer is like, well, it's probably better if you don't. Good. On that, let's have a short break of, well, let's say 15 minutes, and then we start again 1:15. Is that a good idea? Yeah? Okay, good. Let's do that. Just to very quickly, one second, your attention. Just one good question on Zoom. Should we memorize all the formulas like prediction interval? No, no. I mean, I do not. I don't pay you. I don't pay you to be memorization monkeys, right? I mean that, or whatever your favorite animal is. Of course, the most basic formulas, like how to do linear regression, right? I mean, if I spend 2 lectures on it, well, perhaps it's important. But I don't expect you to know every nitty-gritty detail, right? I mean, if such a thing, a prediction interval, is particularly important, right? If you need to compute it, we will give it on the exam. Knowing that the prediction interval is wider than a confidence interval, you better know that, right? I mean, that I'm not going to give you. Good. Okay, now up, go have your break. Good. If you could slowly take your spots again. I have a fighting chance of actually covering today what I... Yes, exactly. It's about 2 minutes. Technically, okay, I'm going to smuggle 1 or 2 minutes. I mean, that's, sue me, right? Good. And it's in your own best interest, because otherwise I'm just going to continue till I'm done, right? And I'm going to lock the doors. Good. Okay, let's continue. Let's continue. Okay, yeah, not muted there. Good. What we've seen so far, amazing, but everything is linear. Can't we make it a little bit less linear, right? Without immediately diving into the deep. Yes, actually we can, and quite straightforwardly. But there's a reason why we started with this stupid linear regression, right? I mean, it's actually way more powerful than you might think. And well, we'll see it in many guises later on again. Let's start with the problem that right now, so far with what you've seen, you cannot directly use discrete or qualitative predictors, right? We've seen, for example, in for age, years, I mean that income, credit limits, I mean that expenditure, I mean ads in TV, radio, and whatnot. But there's also qualitative ones that are more like, well, yes or no, or this one, or that one, right? I mean, red, green, or blue, but not a combination and nothing in between. How can we factor this in? Well, relatively straightforwardly, and probably your best guess would have already come quite a long way. If you have a binary predictor, you can simply use a dummy variable, where the dummy variable takes a value of 1 if the value holds, and the value 0 if not, right? That's the one option. And I already skip ahead a little bit. We could also do it the other way around, or the other way around. I would do 1 for the one value and -1 for the other. Potato, potato, doesn't really matter. What do we get? We now get a model. So yi is beta naught plus blah, 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 where the meaning of this beta 1 for this special variable, right, for xi, x1 in this particular case, essentially comes down to we have a predictor. If we predict yi by beta naught plus beta 1 plus noise for epsilon, if somebody in this particular case owns a house. By the way, this example is, I mean, I updated the slide, so if you now have been reading the old book or looking at the old slides, like, oh my God, where is my gender? Right, this used to be gender, right, male and female, and that's in the new book they decided that the best replacement is house ownership. I'm still looking for the ultimate replacement, but I haven't gotten there yet. And the things that I came up with were, well, perhaps worse than gender. In that, so we're now in house ownership, right? But in this now follows the new book. So. And you either do or do not own a house, so that is at least binary. Now what you see is that beta naught in this model is now just simply what is the average credit balance for somebody who doesn't own a house, and well, beta naught plus beta 1 in this particular case is then the average credit balance for people who do own a house. Right? So that's how you can interpret the coefficient. So it's not really a slope, it's just an offset that you get, right? Well, like I already showed you, we can also encode it as 1 and -1, or any value and minus any value, right? I mean, in that sense, it doesn't really matter, but just interpretation becomes a little bit more convoluted, where you now have beta naught plus beta 1 plus whatever the error is if somebody owns a house, and minus beta 1 if they do not, which means that beta naught is the average credit overall, and beta 1 is then the offset. So how you encode your coefficients, that has an effect, but we can relatively straightforwardly use binary variables, right? How do we now deal if we have a variable that has, like gender, right? I mean, there's not 2 values, right? And let's not make it too fluid, right? We have then 3. Well, that used to be ethnicity, right? It used to be, I mean, Asian, African, Caucasian, whatnot. I mean, that's 2021, so they also updated this. And again, I don't like the example. I mean, now, so particularly I feel discriminated because I am from the north, right? And right now we have south, west, and east, right? And we don't have north. Anyway, stupid joke. How can we encode this? Well, we essentially use the binarization trick, but then just twice. So if we have 3 values, we need to use it twice. Why twice? Well, what do we have? So here we have an xi1 for if somebody is from the south, and 0 if they're not from the south. We have 1 if somebody for xi2 if they're from the west, and 0 if they're not from the west. Well, if you're neither from the south nor from the west, then you have to be from somewhere, right? And that in this particular case, I don't think the authors have ever seen a compass, but okay, you're from the east. Huh? Good. I find it particularly lazy, I have to admit. They could have come with so many cool examples. Now, how do you interpret the resulting model, right? So overall, you just have a very straightforward linear regression model. You know now exactly how to fit it. The value beta naught plus beta 1 plus the epsilon is the prediction if you're from the south, and so on and so forth. So this means that beta naught is the average for people in the east, right? The one that I did not encode here, right? So if both are 0, then this one would be 0, this term would be 0. Then we have just beta naught, so that's from people from the east. And then beta naught plus beta 1, respectively, plus beta 2 are for south and west. So this is how you can interpret it. Relatively straightforward, right? And of course, you can expand this to almost arbitrarily many values. Of course, the more values you have, the more data you will need to have, because otherwise you have too little data to actually tease out the right values for all these betas. Right? That goes without saying. Yeah, so testing the significance then, essentially, I mean, well, nothing really changes. What we see here, this was actually previously we saw here, that for the ownership, right, I mean, previously gender, hey, it does not matter at all, which is actually why I didn't think that gender was that bad an example, because the data here shows, and the data is real, it doesn't matter. Okay, that's good. Same thing for where are you from, is also a completely nonsense factor in your model. It's completely insignificant, right? Which is good. I mean, if a bank applies anything else, then they should be sued. So at least this bank will not be sued. Okay, so now we know how to include linear continuous value or continuous valued variables. We know how to do discrete or qualitative attributes, right? So we know a bit more. How about if the relationship between the attributes, right, between the predictors, is not truly linear, right? If it's not just additive, a bit of x1 plus a bit of x2 plus some noise is y, right? I mean, maybe it actually is more like, well, there's an interaction going on between x1 and x2. Like we saw, the banana shape we have here on the slide again, between TV and radio. There seems to be something going on. Well, one thing that you can do is just simply incorporate the interaction term. My God, this is abstract. What is an interaction term? x1 times x2. We can do this, no problem, right? It just becomes, in the end, I mean, well, we don't have it as a column really in our data, but we can easily generate it from the data we have, right? We just have a column x1 times x2. Well, linear regression doesn't care. It's a honey badger in that regard, right? It will just get the coefficients out. So you now get the coefficient beta 3. Can we also do x1 times x2 times x3? Yeah, go wild. Can you do x2 squared? Sure, why not? And so on and so forth. What we are doing actually here, I'm going ahead a few slides. The way you can interpret it, here it says x1, but it doesn't really say x1. What it actually says, it's a function over x1. And the function that we happen to have here is the identity function. It's a very stupid function, right? Same with all the others. So the beta 3 is essentially, let's say, a function over, well, you could say x1, that secretly squishes in x3. Or the other way around, right? Depending on how you want to write this out. What we are essentially looking at, we have a set of basis functions that we apply over our data that then go into the linear regression. So for beta 1 x1, that is the identity, right, over x1. The basis function is out of all predictors, give me just the value of x1. For the second one, just give me the values of x2. For the third one, well, x1 times x2. Essentially a function over all predictors that you have, right? Each of these instances. And what set of basis functions to use, it's up to you. Well, just like me, I have no clue, so let's ask the domain expert, right? But you can already see that we can essentially do all sorts of polynomials, or go completely wild. You can do exponentials, logarithms, mean squared exponentials, and we can just essentially try each and all of them, and then see which one is now significant, which leads to the best fit. Hey, all of a sudden, we're not doing linear regression anymore. Well, actually, we are. Under the hood, we are. But we can now find functions that, the mappings between x and y, that are anything but strictly linear. It's pretty neat, right? Just with the same old machinery that we saw before. How do you interpret the coefficients? Well, yeah, just like that. So essentially you have here, let's ignore this one for now. We have beta 1 times x1, just like we had before. We have and the beta 3 for the special thing over here is essentially how much of beta 3 times x2 times x1 do we want? You can just rewrite it a bit. So this allows you to still interpret things both directly, as we have at the top, which is my personal favorite, as well as in the bottom if you want to make things complicated. Okay, just as an example, I mean, does this also work in practice? Yes. Let's see what we can do with the banana. Well, our expert says, I looked at the data, maybe there is something going on with the TV and radio. Let's add it in, right? So we now have a beta 3 radio times TV. Let's see if this helps anything. And what we see over here in the table, so what are the coefficients? Well, TV and radio gets a ridiculously small coefficient, right? Well, just like Yoda said, I mean, size matters not. The standard error is ridiculously low. So hey, there's really something going on, right? But T statistic at 20. Well, I have to admit, I also forgot what the cutoff was cutoff is at which it becomes significant, but 20 is high. 20 is going to be significant. I can promise you that. The p-value here, you see it, ridiculously low. So yeah, there is definitely banana in space, right? A TV radio banana. Okay, cool. You also see that the R squared, 96.8%, the variance is explained. So this is very close to 100. We have an almost perfect fit. Okay, it's pretty neat, right? With just stupid linear regression that you can essentially compute on the flip side of an envelope. Yeah, okay, but there's strong evidence. I mean, you'll buy it, right? I mean, I don't have to go through that. Up, all terms are significant, yeah, whatever. Good. Now, what if there's, I see a question, I think. Yes, hello, Deborah. Yes. Yes, exactly. You can interpret this directly as magically creating a new feature. And we call this then the, well, that's we can't call it really X3. Well, that's essentially what, how should we call it? I mean, that's Z. We're going to call it Z. And we're just going to start counting from 1 again. We just created a Z1, which we define as the product between TV and radio. That's how you can indeed interpret it. And well, rather than just focusing just on products, like I said, you can apply any function that you can dream of. But the problem is that, well, imagination is limitless, right? Just like stupidity. So we can come up with way too many functions, or way more functions than we can possibly test. So yeah, we somehow need to curb our enthusiasm, and how to do that, well, we'll see this in a future lecture. But indeed, you can just see it as a pseudo feature. What about interaction with qualitative variables, discrete valued variables, or nominal ones, different names for them? Here, for example, how does the being a student or not now affect our model? When I look at this data, I have to admit, I think that the balance of students and non-students there, red and blue, is flipped around. And at least when I was a student, I used to make less money. I had less money than right now, but hey, perhaps I'm particularly good at saving these days, who knows? So how does it now essentially mean? Well, how does it come about, and why should we be careful here? So this is the standard encoding of a student yes versus student no, right? So we have beta naught, that's the offset, plus beta 1 times income, plus some beta 2, which if you're a student or not, right? So that's an offset. And as you see in this data, let's assume that the data is correct, right? I mean, let's believe the data. This beta 2 is essentially just an offset, right? It's exactly the same line, just offset a little bit, because that's the only thing beta 2 can do, right? It can just add a term or subtract, right? And that's if students are indeed, as in my recollection, poorer than people who actually work, right? It should be below, then it would just be a negative term. But it might also be some interaction, because some of you will actually have a job and some of you may not, right? And there might be something going on. So if we now allow for an interaction model, how can we do that? Well, just by creating a pseudo feature. Is somebody, I mean, as a student, what is the student income? So what, allowing a subset of just looking at those people that are students and looking at their income as a term compared to everybody else. This is how you can interpret it. So what you then get, you get a basic line with slope beta1 for income, and then a second term, beta2 plus another slope for students. Well, students have less time to work, right, because they also need to study, so that will adjust the slope. What we now get is something that looks a bit more realistic, that, well, we have two lines that basically students, the income does not develop exactly the same as people who do not study, right? Whether the slopes of the lines is realistic or not, I mean, I leave that up for the experts, but we now get different slopes. Essentially, almost nothing happened here, right? I just allow an interaction term. So now we have this beta3, which is studentship times income. That's essentially what it comes down to. Okay. Nothing spectacular. Okay, now, I already gave away what I'm now just going to tell, but let me actually quickly look at the question. If we continue, will there be an intersection? Yes, absolutely, absolutely. I mean, that's so. Then if students and non-students make more than 150, whatever this is, I think this is 150K US dollars. So if you have particularly rich students, then yeah, at least the line would have the method would have evidence to continue the line in that direction. Whether this is realistic or something else. Let's make it more nonlinear, because right now we just took a linear combination of x1 and x2, right? And we called it then z1. But by the values, it may create some, it may make the line a little bit more spectacular, but it's not truly nonlinear, of course. But I already gave the secret away. We can essentially consider all these x's as a basis function, right? It's just a function over all inputs, all predictors that we have, and we just happen to have chosen x1 verbatim. But we could also have chosen x1 squared or whatever. So now let's take a step back. Let's not get ahead of ourselves. Let's consider simply polynomial functions, polynomial expansions as our set of basis functions, which means that we consider x1, x1 squared, x1 cubed, and so on and so forth, right, up till the order of the polynomial that we're comfortable with. Now, each of those models, so polynomials up to order 1, up to order 2, and so on and so forth, we can test. We can see, okay, how good is this? Was this now significant, yes or no, right? And so on and so forth. You know all the ingredients. And what you now see is that the prediction that you get, and of course you get a more squiggly line the higher the degree of your polynomial. So a linear fit would be this ochre, this dark yellow line, whereas the data, as you see, I mean, it again looks like a banana. So the blue line is a much better fit. That fits actually quite nicely. That's I think the quadratic one at the top of my head, or possibly the cubic one. No, it's the quadratic one, yes. And the green one, up to the power 5. So we have squared, cubed, quartered, I don't know, and quintic. I mean, that one I think I remember. That fits the data too well, right? I mean, that starts to really overfit. What you then actually also see if you go to, okay, not on the slide, but in the book, I think they do get the numbers. You will really see that the R becomes too good. And if you look at the significances, they drop down. So no, we should not go there. We should be really, really careful. Okay, this particular case, what did we do? We went from strictly linear to have a polynomial set of basis functions. All of a sudden, we can fit squiggly lines, right? And we can make them squiggly. Okay, pretty neat. So should we use, question on Zoom, should we use degree 2 or 5? Well, let's do a raise of hands. Who thinks in the room, I'll give you the answer in a second, Lo, may not, because you can't see the room. Who thinks we should use a degree 5 polynomial to fit this data? There's not a single one who wants to humor me. Okay, who thinks we should use a polynomial of degree 2 for this data? Okay, Lo, I mean, just, what is it, who wants to be a millionaire? I mean, we just asked the audience, and the audience says degree 2. And I agree with the audience in this particular case. That's the one that fits the data snugly, but not too snugly. And it's a much better fit than the linear one. If we now look at what are the significances, right? I already told you, okay, it's going to be significant. Well, we see that the intercept, of course, is significant. I mean, that would be stupid if it's not. Horsepower by itself, not so. But horsepower squared in this particular case, that's a pretty high t-statistic. I think 5 was the cutoff at the top of my head. I mean, not, but this is pretty good. P-value, very, very low, right? I mean, that's let's go for that. Good. Okay, that was it already for how we can, well, non-linearize linear regression. So went over it really quickly, but there's really not so much magic to it. Just dream up a number of functions, apply them to your data, consider them as pseudo columns, throw the machinery at it, it will do its thing. Now, said your imagination is almost limitless, so you will come up with many, many functions. So we need to pick out which are significant. Well, hey, that is the subset selection, the significance testing. I already gave you, or equipped you with all the things that you need to know to, well, now do essentially nonlinear regression, right? So pretty good. Doesn't mean that you're ready for real life, right? I mean, that's so if you come across some real data, you should still be scared, right? And that's so. Let me tell you what you should be scared about, and how you can detect and perhaps prevent any mess that you might get yourself into. The first problem is that the data that you're looking at may not be linear, right? And not linear regression, we assume the data is linear, and then Gauss-Markov, okay, well then we can find the parameters. But if it's not, yeah, then we're screwed, right? High bias, nothing we can do. I already showed you how one way how we can detect if we're in nonlinear land. Look at the data, right? Well, that's one way. I mean, that's sometimes you have more than two variables, input variables, and then you have an output variable, so more than three. I don't know about you, but I always have difficulty imagining four-dimensional spaces, and 20-dimensional spaces. I mean, that really blows my mind, right? I mean, and that, yeah, well, you're not the only ones. What we can do, however, is one simple trick. Doctors hate it, as they say on the internet. We can always look at what are now the residuals that we get, because no matter if we have 20 predictors, right, and all the coefficients we fit them, we can actually look what are now the residuals. And if for any of the input variables we now get a weird shape in the residuals, and then something fishy is going on. So what we have here is the residual plot for the mileage per gallon. I mean, that's a very American book. And as you can see, the residuals, well, they are zero mean, right? They're centered zero. That is good, right? I mean, that's what the method does, right? We want to get the prediction as close to zero as possible. We again want to get the spread as small as possible. And this is essentially what, with this model, it can do. This is it. We've already seen that horsepower squared would be a much better fit. Now, this V-type shape is in this particular case an indicator that, hey, okay, something nonlinear is going on. Does it always have to be this V shape? No. It essentially, as long as it's not a nice straight band around this dashed line around zero, right? So there can of course be some spread because there's some irreducible error, right? Sometimes that's the best we can do. But the moment that there is some structure going on in the residual plot, then your alarm bells really should go off, right? So my first tip of the day, look at the residuals plot. I am not going to explain you how to draw a residuals plot. Consider this as an exercise for the interested audience member, right, or in the interested student. I have in the past asked students to draw a residuals plot for a given set of data and a regression line in an exam. Not all students were able to do so. They may or may not have passed the exam. That I honestly don't remember. So this is a really useful trick. Make sure that you master it. It is very easy to draw low. Absolutely, absolutely. It's not very hard. Hence, I was surprised that not everybody could do it. Yeah, okay, so the U shape, I mean, or any type of weird shape is bad news. For example, here, if we now do include this quadratic term, horsepower squared, we already saw it had a much better fit. The residuals plot looks like this. Ignore the red line for now, right? That's the spline that we fit, okay? It shows, is there any residual structure left? So if you think away the red line, this looks much better, right? This is nicely centered. You might say there is a bit of a spread, right, around, so the fitted value is 10 to 20 or 15 to 20. It's a bit wider, right? I mean, it's not perfect in that sense. There's still something that is left unexplained, but overall, this is pretty good. This is pretty good in that. The red line, like I said, actually not like I said. So this is in this case a spline that we fitted over this. Doesn't really matter. You can use anything. I mean, that is non-linear. In the moment that is not a straight line, then you should be worried a little bit. Closer it is to a straight line, everything is fine. We will go to the nonlinear methods in a few weeks. Okay, so another problem that you will encounter, and you say, I will not. Oh, yes, you will. Error terms will be correlated. And as you know, I mean, from the very beginning, we made a number of assumptions, right? The world is linear, right? I mean, there is a linear function generating the data. Okay, amazing, right? What is the noise? The noise was Gaussian, right? I mean, zero-centered, right? I mean, varies. Okay, amazing. One of the assumptions we also had is that every data point, and hence every noise essentially, is drawn independently and identically. They're all drawn from the same noise distribution, right? And that is the cornerstone assumption of essentially all of statistical learning theory, which is pretty much the only theory we have on how to extract structured data. Some people may be very angry when I say that. Okay. Now, could it possibly be that this IID assumption is broken? Yes, pretty much all the time. All the damn time it's broken. And in certain cases, this is kind of okay and it still works. But sometimes it is so horribly broken that, well, whatever model you tease out of your data, it's going to be completely rubbish in practice. So this is one example. Let me first take a sip. Let's first preempt a little bit. What could possibly go wrong? Well, if the assumption, our modeling assumptions are broken, our conclusions are going to be shit, right? That means that all the things that we think we see may be completely spurious. So predictors that we think, oh my God, this is so significant, maybe complete nonsense, right? We think, okay, oh, my method is so precise, maybe nonsense, and so on and so forth, right? When your modeling assumptions are broken, basically all bets are off. Let's give an example. We double our data, right? Imagine your favorite data set, and we just double it. Now, if we're now going to estimate our parameters, we will hopefully get the same estimate, right? Coefficients will be the same. The confidence intervals, what will they look like? They will actually shrink because we have more data. We have the same value, more data. Amazing, right? I mean, we're super happy. Should we be happy? No, because we just simply doubled the data, right? I mean, otherwise we could just double it again and again. Oh my God, we have confidence values. I mean, they're point estimates. I mean, amazing, right? Something is off. What is off is that the noise that we have in this doubled data, they are not drawn identically from the same distribution all the time, right? Because the first real row and the first copy row, they have exactly the same draw. We have twice the same noise. So it's not the same as drawing a data set that is twice as large from the same distribution, but just simply doubling. So what we have achieved by just doubling is that all of a sudden the noise terms, they're correlated, and they should not be, right? And hence the machinery starts to falter. Another setting, but it's very easy to see that, hey, it may not be such a great idea to just go forward, is in time series. So if we have data that is temporal, in most time series setups, the data we have now for today is highly predictive of, well, the next time point, right? For example, if you were to predict, you're now a computer vision algorithm, and you have to do post-estimation, right? You have estimated, okay, he's holding his hands up, he's trying to balance or something like that, right? Then in the next frame of the video, well, what will the pose be? Yeah, well, probably roughly the same, right? I mean, that's unless I fall really spectacularly, I mean, okay, and then you have to re-estimate, right? What does this mean? That between each of the individual frames, well, the errors are dependent, right? By your first estimate, then not so much is going to happen, right? And so they're not drawn completely independently. It's not like a data set of all possible poses that I could take. Suppose that we now look at, what is this? Suppose that it's temperature, right? Let's say daily temperature, and not over time. Well, winter, right? It gets cold, right? And then spring, and it gets warmer, and summer, oh, it's hot. And then if we now take a random day, and you just say, okay, what is going to be the temperature? Just predict the value from yesterday, and you're often quite spot on, right? Whereas if you would just predict the average temperature over the entire data set, yeah, that would be a pretty bad estimate. And that is essentially what linear regression is trying to do. It's trying to find, it's basically trying to predict as if there's no dependency between two adjacent data points, right? Basically, we shuffle all the data, and that's what it wants to predict. So the moment that there is some structure between data points, between errors, you're in trouble. You're in trouble. But, And well, in time series is easy to see, right? The post-estimation thing. You also have this in many other cases. And that's so one of the prototypical ones right now, I mean, that people are looking into in computer vision. You have a picture of, for example, a cow, right? I mean, that's, or you have like a whole database, ImageNet, I mean, lots of pictures of animals and other things. And you have now a computer vision model that can detect cows like a mother F, right? I mean, really, I mean, it's easy to go, cow, right? 99% accuracy, perfect, right? Until you show it a picture of a cow on a beach. No, so like, okay, I don't know, what is this? Because it turns out it didn't learn to recognize a cow, it just learned to recognize the correlations between, hey, there is some green and there is some blue sky maybe, and there is some, well, some whitish, blackish thing, right? I mean, yeah, well, if that whitish, blackish thing is now on a beach, there is no green, it cannot recognize it. So there is now a very strong dependency in what it learned that should not be there, right? So all of a sudden, data is not IID. Lots of ways this can go wrong. So be very careful if your data is now IID or not. And if it's not, well, run for the hills. Third, so this is actually one of my favorite slides, because you see this all the time. And ridiculously many machine learning methods cannot deal with this. So there's a lot of cool research to be done. And it includes my favorite word from statistics, namely heteroscedasticity. Right? And try saying that 3 times quickly after one another. What is heteroscedasticity? This means that if we now just look at the plot, the errors, they are nicely zero-centered, right? Exactly what we wanted, right? There's no banana or any shape in any other shape that we can see that squiggles around. But the spread of the errors is not constant. It is not a nice band, right? In this case, it looks like a funnel. It could look like well, I know, an hourglass, right, on its side. I mean, it could do wobbly, wobbly, wobbly. I mean, it can do all sorts of things. But the moment that it does not look like a straight band, we have heteroscedasticity. That means that for certain input ranges, we have a different noise distribution than for others. And what are we assuming? Well, we are assuming that all our errors are IID. There is one distribution that generates these epsilons, and that's that. That's clearly not the case, right? It's not independent of the input values. You now, in order to predict this data well, you magically need to know what is the input value, and then you can, okay, we're in the lower range of X. Well, then I'm going to use this distribution, and so on and so forth, right? There's more going on. Heteroscedasticity is, you see this in pretty much every real-world data set. And like I said, most machine learning methods can't really deal with it. Why this is the case, I don't know, but it makes for a lot of fun research, especially in my case for causal inference. Okay, so yeah, so often you can just transform your input variable or your the target variable a little bit. I mean, that's you can detect it and then you can scale input or output. You can hack your way around it, but none of this is something that you would really want to do on real-world data, because it seldomly looks like a nice funnel, and then you could stretch it out perhaps. Typically, it looks like a very weird shape. And then you would first need to learn the weird shape, and then well, straighten it somehow, and then, what on earth are you doing? I also don't know. Okay, fourth problem, outliers. Another thing that somehow in machine learning land has been ignored for eternity, and is still being ignored very hard by most methods and most researchers. What is an outlier? An outlier is a point for which in our case, the prediction is really far, the outcome is really far from the prediction, right? It's a strange point. You can also call it an anomaly. There's tons of definitions, I mean, all of them mostly informal. Mostly these points are generated by a different mechanism than what we see most of the data being generated by. These points are problematic because depending on how you fit your model, right, so this point number 20 will have a huge error. So this means that if we now have, we minimize residual sum of squares, well, the square of this error is enormous, right? Much larger than all these small distances. So essentially this one single point already drifts the model away from where we want it to be. Okay, that is bad, right? I mean, you see that the red and the dashed line is just the red line minus 0.20. It's already shifted just by one little point. That is bad news. So what most machine learning methods assume is that you first, or you ask the expert, but you look at the data and pick out all these weird points such that, well, we have nice and clean data. Let me let you in on the secret. Data is never clean. It's always full of outliers. when we have no idea in which direction or where they live. Or it's really a true problem. If we look at the residuals plot, it's very easy to spot outliers, right? So that is actually a very nice tool. So again, if only you were to know how to draw a residuals plot, we can just spot those that are very far off. So hey, this may be interesting. Okay. Yeah, so one of the things that you can do to determine is something now an outlier, or is it just a point that's just a little bit further away than I would like it to be, you can standardize your result. You can also call it studentize, because it's students distribution, but I call it standardized. Basically, you fit a Gaussian over your data. You divide by the standard error. That's roughly what it comes down to. So here, it's each residual divided by the estimated standard error. Now, by dividing by the standard error, essentially we say, you shall be Gaussian. Nice thing about telling something that's Gaussian, well, they take the shape of a Gaussian, and we can use a Gaussian distribution, just like we've been doing for the confidence intervals, and et cetera, to now determine where does a point lay. So this point 20 is now at 6 in a standardized. So that means it's 6 standard deviations away. Well, that's ridiculously significant. It has a really, really, really low p-value. So that is definitely an outlier under this assumption of Gaussianness, right? So this is one technique that you can do by just standardizing or studentizing your residuals, and then throwing out all points that have a value above where you set your cutoff, right? 95% or 1% or 1,000th of a percent, that is typically a good value. Okay, now, final topic, I think, at least, I can only see one slide ahead. So outliers are annoying, right? And then they shift the prediction, but they didn't screw up everything. The first lecture I already asked you, what is the worst possible point that you could add to a data set, right? Perhaps you remember. Well, those points, they often exist in your data already. You don't have to add them yourself, right? You don't have to look angrily at the cybersecurity student next to you who's trying to poison your data. These are called high leverage points. What is a high leverage point? Well, let's first think, here, point 11 is high leverage. Number 20, that is just an outlier, right? You could say both are outliers. Why is point 11 now so special? Well, point 11, it is 11, or 41, sorry. So under this angle, it looks like an 11. Point 41 is a value of x for which we have very little evidence. Whereas point 20 lays in a domain of x where we have lots of other data samples that also have a value of, around 0, right? So it's so point 20 comes from an area with a relatively high density of x's, whereas point 41 comes from an area with very low density of x's. What does this mean? This means that linear regression, and also many other points, they will sort of, like a crazy Jack Russell, hunt after this ball, like, oh my God, yes, that's the ball. I need to fit one. I need to fit it. Whereas point 20, it can kind of choose to ignore, because there are so many other data points at this value of x, right? There's so many other balls that the Jack Russell can hunt after. So it will leave ball 20 reasonably behind, reasonably after. So high leverage points are outliers far away, or relatively far away from where we have other data points, right? Really at the shoulders of your data. And those are dangerous because you can see with the red and the dashed line, they have a high leverage. They can really change the slope of the model that we fit. So those are the outliers you really want to get rid of. So you have some ways how to determine them. Leverage statistic is one of them. That's essentially you fit a Gaussian over the entire thing. That's what we have here, right? The oval is essentially a two-dimensional Gaussian. And then again, standardize, because hey, it's a Gaussian. We can see, okay, how far away are you from the center of the Gaussian? How many standard deviations is that? And we can just cut it off, right? In linear regression and in most of machine learning, everything looks like Gaussian. You have one other interpretation, is that the per point, so for which you could compute this leverage statistic. So HII, for the ith data point. Now we look at in the hat matrix, we look at the ith diagonal value. Well, what was the hat matrix again? That was basically this linear algebra combination of input and output, and how we can compute what is the optimal vector of betas, right? What are the optimal coefficients? The higher the value of this HII, this diagonal, it essentially shows what is the contribution of this one point to the coefficients vector. So if you have a particular high value in this hat matrix, well, that has a really high contribution. So those are the data points you should be very careful of. Well, given that you already compute this hat matrix in order to get your coefficients, it's relatively straightforward to spot these bastards, right? You don't even have to look at the residuals, right? Still, do look at the residuals, always. Okay, last. Okay, this is really last, and then we're done. I really lack, like, I should have like an overview of 3 next slides, then I would be good. Okay, so collinearity. This is the problem that you will face in any non-trivial data set, right? What does it mean? That we have 2 predictors that are not, well, independent, but they are strongly correlated with one another. So I would call it correlated inputs, but collinearity is what they call it in statistics. Sadly, I missed the meeting where they voted on the name. For example, what we have here, so age and credit limit, okay, not collinear, so they do not correlate, but credit rating and credit limit, you know, what is your the spending limit or whatever, they correlate, right? I mean, the higher your credit rating is, the more the bank will allow you to borrow, right? I mean, so that goes hand in hand. What does this mean? This means that if we now want to predict something, right? So for what are we interested in predicting here? Well, we're interested in predicting something. I don't even know from this example. It doesn't really matter. Because we now have 2 attributes that strongly depend on one another. And whether my model now chooses the one or the other is a bit potato, right? Perhaps it can predict a little bit better with this one, and then it will not use this one. The other one becomes insignificant, or the other way around. Well, you could say, okay, well, yeah, screw it. I mean, as long as I can predict well. But if your goal is inference, you want to learn what is now important in out of the predictors I have, this is really, really bad news. So what you see here, for example, that the one model, so where we have, on the intercept always, we have age and we have limit. Look, spending limit is super significant, right? Amazing, we really, really want it. But if we now have rating and limit, so age we kicked out, then all of a sudden, I mean, rating is significant, almost, or barely, I would say. Whereas limit all of a sudden is insignificant. So what does this mean? We will never obtain, unless we really overfit like crazy, a model that will identify that both rating and credit limit are informative. Yeah, but it's not really what you, especially so here, it's kind of okay. But if you want to identify, okay, which genes are responsible for a bad disease, perhaps you want to catch both. Right? Okay. Yeah, pairwise, we can detect it. This is a green star. I mean, you can read this up later. But, up. So this is the slide which I will start with next week. So thank you very much for your attention. See you next week. Bye-bye. So does this, I mean, I guess if it's static, then you can hear it all the time. So if this is currently better, Rifat, you just ask me a direct question, then I know what to do next time. Otherwise, yeah, okay, good. Then I know what it is, and then, well, it's because of the deaf people in the room. I'll try to balance this next time. But let me know beforehand, because this is indeed, I mean, it should be high quality for all. Thank you very much. Hello. Yes.
As far as I know, when we use the F statistics, we assume that our numerator and denominator have chi-square distribution. So the data have the normal distribution.
Yes, exactly.
So when we use F statistics, we assume that all our data points have normal distribution.
Yes.
Or no, in general.
Wait. Okay. So these are always these questions where, because in the end, indeed, everything is Gaussian except when it's not. Yes. So in this particular case, we assume that the residuals are Gaussian distributed. So basically, that's essentially what the F. Let's go back one if I can. Blah, blah, blah. This is very interesting. Okay, so for example, well, where did we have a good example? For example, here for the outliers, right? And that's one where you could do this. So we have the residuals, which here look quite well. They already look quite Gaussian distributed. But if you would project them all to the y-axis, I mean, whether it's truly a Gaussian or not, right? Yeah. Let's not split hairs, right? But now, by assuming that it is indeed Gaussian distributed, right? We standardize it, and now we can apply an F statistic on this. But the main idea is that we now really assume that the residuals are Gaussian distributed, and that allows us to draw conclusions under it. So we don't assume that the data, like all of the data, is Gaussian distributed. Essentially, here we assume that the residuals are Gaussian distributed, which means that we essentially assume, we hope that our assumption, underlying assumption, we have a linear model under the basis function that we have, and then some Gaussian noise around it, right? Epsilon is zero mean, and well, and of course, in theory, I mean, it could still be zero mean, but look like this, right? Let's say this is a Poisson or something. Poisson is discrete, okay. But let's take a Poisson, an exponential distribution. You could still have a zero mean, but a much wider spread in one direction.
Yeah, like when we have lots of data,
yes.
we
exactly. 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 Yes. So that is neat. That's neat how it is. So it's not so much that all of the data is Gaussian, right? It's just one Gaussian blob in some high-dimensional space, but it's more like what is left of the data after we extracted all the linear structure that we assume to be Gaussian.
Okay.
And now you also come to the bias term, right? So if that is simply not true, then it might look Gaussian, what we have left over, but that may just be because we fitted it so badly. Yes. Exactly. Yes. That's,
okay, and
yes. Exactly. Exactly. Yes. Exactly. So for Gauss-Markov, it's basically the distribution of the predictors. That can be anything, right? So the distribution for each x and combination of x's can be really anything. Go wild. As long as there exists a linear function, that's what Gauss-Markov assumes, right? I mean, from the predictors to your target, right? Your predictor, the one you want to predict, to y, and then with a Gaussian noise around it, around this predicted value, which, and this is now why, the correlation of error terms, why this is so important. And Gauss-Markov really breaks down the moment that your data is not IID. Because then the Gaussian distribution, yes, it is Gaussian distributed, but if it's not IID, then
we don't have correlation.
Exactly. Exactly. Yes. Okay. Thank you very much. Hello. Yes. That is what we discussed last week. So we had first the linear regression with just one predictor, and then there was some relatively easy way to just write down how do we estimate beta 1 and how do we estimate beta 2, right? That was just a given formula. That is just for one predictor. Now, if we have multiple predictors, then the formula sort of breaks down. Actually, it doesn't. I mean, it sort of expands into this linear algebra thing where we take x times x transpose times, well, I wish I would have to look at, well, that monster, that is the hat matrix. Right? So if you just compute this thing and, well, you want this hat matrix because it puts the hat on y, right? Remember? This thing essentially computes for you what are the optimal betas. Now, if you were to look into this matrix, then you look at the diagonals, and then you look, where are we? Here, the leverage point, where was it now? Here, yeah, exactly, here it was, yeah. So 0.41 in this particular case would have a very high value on this diagonal because it steers the beta a lot. Basically, it needs the beta to be more far away from where the others want it to be, and hence the hat matrix diagonal value will be high. Yep.
All right, thank
okay.
you.
Yes. Yeah. exactly. It's essentially, it's irreducible error. Yes, exactly. Exactly. Yes. So, and like for this, in the example with the cow, right? I mean, that's then if we only have pictures of cows in meadows, then in a way, well, what we're asking the machine to learn is not to recognize cows, but well, cows on meadows. And a cow in space or a cow on a beach, yeah, well, that is not drawn from the same distribution as the cows it has seen. So it has learned the distribution of cows on meadows, right? Yes and no, but let's call it, it's extremely painful. It's extremely painful, and it's really like cutting edge research, right? Whereas what we're discussing here right now, this is a basic course, right? This is essentially stuff that we know already since decades. But the fact that this problem, right, this IIDness was solved, well, it's not even solved. I mean, we're just scratching the surface, let's say last year. It shows you that, well, this is anything but outdated. But, yeah, okay, very good. Yeah, and how do you test this? Yeah, that's yeah. So and same thing. So all the problems that you have right now with deployment of algorithms in practice, right? All fairness discussion, whatnot. Also your credit ratings. And that's so. Should it take into account ethnicity? Well, no, right? But okay, if we now just take away the factor ethnicity, is now everything good? No, because often it's the case, and so in the US, I mean, you have plenty of examples where there's lots of segregation going on. So if I now have your postal code, I know exactly if you're snowy white or this or that or Mexican or whatnot, right? So my method, at the moment that there's income differences or whatever differences between these groups, historically, we don't want them to be, but historically, but we now ask the method to predict as well as possible what is the case, yeah, it's going to exploit this. Right? I mean, stupid. No, the method is doing exactly what we asked. The data is stupid, right? The history is stupid, right? So yeah. So what we in a way should do is we should now, in a way, in a magic way, incorporate ethnicity or other. I mean, let's say, well, gender or sex or whatever, right? I mean, that's features that we don't want to discriminate against, and we should tell the method, well, predict as well as you can, but don't do anything or don't predict anything different than if the same person, like if we would turn you into a woman right now, right? I mean, then the outcome of the method should stay the same. If we change the skin, just output should stay the same, right? Otherwise, it's just it's illegal, right? It's not just bad science and bad practice. This is again what is happening right now. We're at the cutting edge of research. So any method that's being deployed right now, I mean, I'll be very wary of it. Be very wary of it. And that comes to the, well, is your data now, is it IID or not? Even the fact that if we move away from this fairness, in the cancer example, right? We have this population, and we have this drug that is then, well, really good for some of the patients and really bad for others. Well, it's not IID, right? That's the whole point. And what is now that group? How can we catch those people for which it is IID, right? Where basically it is a coin flip for whether it's now going to work or not, right? And for these people, when let's say it is active, for this it would be really bad. Yeah, I want to split my data into two parts, such that for this, okay, we know that, well, it would be bad news, right? This is IID, this is IID. How to split your data into IID groups. We had a paper on this published last year. Again, scratching just the surface, right? I mean, so lots of really cool research questions. You're welcome. Hi. In the lectures, no, because I don't speak R. Exactly, and the practical stuff, that is in the tutorials. In the exam, we have never included any pseudocode, any R in the exam. That's what I can say historically, right? I mean, I can't predict what we're going to do, right? I mean, but now it's your. I mean, that is the book. That is the book. So, and the practical assignments are there to, well, to give you a chance to put into practice what we explain in theory, to see, like, does it work or not? And of course, that we need to be able to grade. And for that, we need to choose one particular language. and the language that the book uses is kind of convenient, right? So if it would have been statistical learning with Python, then it would have been Python. If it would have been with C++, then with C++. Would have been with Java, then well, too bad for you. So that is the general idea. Yep. Mostly. I mean, I always need to keep a bit of some room for error, right? That yes, that's indeed, yeah. So if you can do those with your eyes closed, then you don't have to be afraid of the exam in any which way. Yes. So I leave it to your discretion. So this is not the first course you're taking, right? It's not the first course that you're taking. So you kind of know, like, yeah, here, yeah, okay, good. So that's so we don't care here in Thailand, I mean, about students who can memorize very well, right? I mean, that is not what we're testing. Plenty of universities, that is what's being tested. We don't do this. At the same time, so if I give you some data points over x1 and you give some data points over and y, then I hope that you will be able to think, okay, so beta naught, beta 1, I can estimate it like this and this without me giving just the variables. Do I expect you? Will I probably expect you to compute the leverage of an individual point or to compute the hat matrix? Most likely, no. Most likely. What I want to test in the exam is, can you think? Can you reason with what I taught? I don't. That might be, but I'm much more interested in, like, do you understand it? And I am very little interested, can you reproduce? Exactly. So, and of course, if there is then an important formula that is larger and that we can't really expect you to know, yeah, well, then we're not going to ask you to spend your time, okay, well, apply this formula on some data, but maybe we ask, okay, well, hey, this is the definition of a Q statistic. I've never seen a Q statistic. Explain how this relates to a T statistic. Well, that you should be able to do, right? So here I've seen a T statistic, you know roughly what it does. That's right. Yep. Good. Okay. Yes. Yeah. Okay. Yeah. 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 That is. So what we call this is again a big open problem. People have been looking into this, but this is a big open problem. Let's give a recent example. So, a pandemic breaks out. All of a sudden, the whole fucking world changes. Excuse my French. I'm still live on YouTube, so I mean, I should be careful. So any prediction mechanism that we had that up till when did the whole lockdown thing happen? Somewhere February. Well, actually, I think it was March 13th. Yeah, that's something like this. And all of a sudden, I mean, everything went to shit. All the predictions, all the models were trained on the old world, right? So let's say price predictions for airplane tickets, just based on this, nobody's flying anymore, right? I mean, and so on and so forth. I mean, delivery prices. I mean, yeah, I remember I was buying I needed a webcam. Everybody needed a webcam all of a sudden, right? All the shops said, yeah, sure, I'm going to have this next week. No, right? It took like half a year to get the webcam. So these are these what we call shocks, right? I mean, if you have your, it's a breach of this IIDness. So basically, tomorrow is very different from from today, right? The whole mechanism is different. So what you have in literature, what you call is concept drift. So you have a certain model, but then you could see that, let's say ice cream sales. Right? We have 10 over the year. During summer, I mean, it will be higher than, but it's not like, okay, now summer begins and now there's ice cream. In winter, you don't sell anything. This is more like a coefficient that drifts, right? In that, so that is the concept drift. And then you also have like stuff, for example, new product enters the market, right? Or new virus, I mean, that upsets everything. So that means that the distribution of the data from that point onward, of the world, right, the mechanism of the world, that changes. And unless you have a method, your method can actually recognize like what the hell is going on here. But yeah. Yeah. Well, all these methods assume that the world tomorrow will be the same as the world today. Or the other side, I mean, this data point is going to be the same as that data point. The way that this is generated, maybe with a slightly different noise just by chance, but it does not allow for all of a sudden, well, like in the cancer example, right? These people do respond positively, these don't, right? I mean, that is actually what you don't want. Yep. Yep. Exactly, yeah. So that's what you do. So I forgot the exact number, right? So don't quote me on it. But let me actually ask you a question. To have a bit of record. How often do you think that Netflix retrains its model? Per day? No, this is the question. Now the question is done. No. How often? Thousands of. Thousands of. Because the moment that something new is available, or there is some news post somewhere that increases the attention for a Squid Game, right? I mean, something new, right? Or something old, and all of a sudden comes back up, right? And that's it. Yeah, exactly. I mean, so now the next season of The Witcher is coming out soon, right? And that well, then all of a sudden you should also start recommending it. Gets in the news. You should recommending Witcher 1 again. People will want to rewatch it. If you just use the model that you used for the last 6 months, you're not going to recommend Witcher, which is pretty stupid. So really, these large companies, they really retrain their models tens, dozens, hundreds, 1,000 times per day, which is insane. If you just also think about how many resources they spend on this, right? AWS is very happy. That's why Jeff Bezos is such a rich man. So, but that also shows that this concept drift is a very unsolved problem. And in a way, what you like, of course, for example, The Witcher, and why did they come up with it? They have heard that it's out, right? I'm looking forward to watching it. And hence, well, as a human, you think, hey, well, that's a few weeks ahead of time. Let's put it into the model. That's because we think about the world in causal terms, right? This will cause attention. That's what I expected it will cause attention for. It really doesn't know that. Look at historical data. People don't watch Witcher or their brother series. So, yeah. So it hence these shocks in a dynamic world that is essential for any business. And almost any machine learning model is completely oblivious to this. Completely. Right? So and these are just like some of the small problems that we have. There's still a lot of work to be done in the whole like the terror vision of Terminator robots being roaming Earth. Nah, not so close by. Not so close by. And, hopefully, never. Good. Yeah. You're very welcome. Cheers, gentlemen. Bye bye. Good. Unless there's questions on the Zoom, which I haven't received. I'm going to stop the share and close the meeting. So, also Zoomers, see you